Welcome back to part 2 of the Page Frame Allocator section of this tutorial. In this video we will finish our Page Frame Allocator so that we can start requesting page frames wherever we need. Alright, let's get started. But before we can lock and reserve pages, we need to create some functions to do so. So back in Page Frame Allocator.h, we need to create some new functions. We need a void free page, void pointer address. We could just copy that one and do lock page. And in our private tag, so we don't want to be able to call these from outside of the class. We only want to call these from within the class. Void reserve page and void unreserved page. So we've got free page, lock page, reserve page, and unreserved page. And this is just going to be setting the bits and keeping track of our used, reserved, and free memory sizes that we have here. Alright, let's make our implementation. So back in PageFrame Allocator.cpp, we can do void Page Frame Allocator, free page, void pointer address. Alright, now we need to figure out the index that we need to use for the page bitmap, and that's pretty simple. So uint64 index equals casted to a uint64 address divided by 4096. Alright, now we can check if the page is already free. So if page bitmap indexed by index equals false, we can just return because it's already false, which means it is already free. But if it is not free, then we need to do page bitmap.set index false. So we're making it free, and now we need to do free memory plus equals 4096 and used memory minus equal 4096. So this is taking a page frame, checking if it is in use, and if it is in use, we're freeing it, increasing free memory and decreasing used memory. Alright, now we need to do the same with lock page. So we can just copy and paste that and change free to lock. And we can change if page bitmap index equals true, return, and then if it is not true, we set it to true, and we minus the free memory and plus the used memory. Now we need to do the same with reserve and unreserved page. So just copy this, copy these two functions exactly, and change free to unreserve, and change lock to reserve. Now the only thing that we do different in the reserve as opposed to free and lock is that instead of using used memory, we used reserved memory. So in unreserved page, we change used memory to reserved memory, and the same within reserved page. Alright, so now we can free, lock, and reserve and unreserved pages as we need, but usually we need to do more than one at a time. So we'll fix that in a second, but before we go any further, I'm just going to compile this to see if I've made any mistakes, just to check my sanity. Alright, so just at line 43, I use index named I here, but I use T here, so just change that to I. And that should be the only problem. Yeah, that's the only problem. Alright, so let's move on and create free pages as opposed to free page. So back in PageFrame Allocator.h, we can copy our free page, copy our lock page, and put an S on the end to signify that it's the plural. And then we need to add a uint64 page count. So this is how many pages we will be freeing or locking or reserving. We'll do the same with reserve and unreserve. And copy in our page count as well. Alright, now onto the implementation. We create a new function. Call it void page frame allocator free pages. Take our void pointer address and our uint64t page count. And now we can do for int t equals 0, t less than page count, t++. Now we do free page, 2 brackets, void pointer, go out of 1 bracket, make 2 more brackets, uint64t, go out of 1 bracket, address, plus another bracket, t times 4096. Alright, so running down what we did there, we converted this address to a uint64, so we can do normal maths on it, adding the bytes of a single page to go to the next one, and then converting it back to a void pointer to pass the address to our free page function. Alright, so we can copy this for lock and unreserve and reserve. So lock pages, change this to lock page. And with unreserved page, we can change this to unreserve and unreserved page. And reserve page needs to be reserve pages. Alright, now we can just compile that again to make sure everything has worked correctly. Now we need to make sure that we can lock the pages of the bitmap and reserve the pages of the unusable and reserved memory. So we'll do locking the pages of the bitmap first. So we need to lock the pages that our bitmap is stored in so that our bitmap doesn't get corrupted because our page frame allocator has handed this page out to another process. So this is pretty simple. All we do is call lock pages. We'll give it the address of the page bitmap, the size of the page bitmap, so page bitmap.size divided by 4096 plus 1. So we're passing it the address of the page bitmap and then telling it how many pages it needs to lock. Alright, so now we need to reserve the pages of unusable and reserved memory. So we can just get rid of this. And we can copy the start of our for loop up here because we need to access the memory descriptors once again. Put in our curly bracket to fix that up. And now we can do if descriptor type does not equal 7, indicating that this is not UEFI conventional memory. We now need to reserve pages, the address, so descriptor physical address, and the descriptor number of pages. Alright, so we're going through all of the memory descriptors, checking if they are not conventional memory, and then reserving their pages. Compiling that to make sure we have no errors. Now we can theoretically print the free, reserved, and used memory on screen to see if our page frame allocator is reserving, locking, freeing, etc. correctly and keeping track of what memory is in use and what memory is free. We need to create some functions to actually get the memory sizes because we don't want to access this memory directly because then we can set it and that will cause really bad problems. So we need to create some getter functions. So that's pretty simple. We have uint64t get free RAM, uint64t get used RAM, and uint64t get reserved RAM. We can copy these 3 functions back into pageframeallocator.cpp, go down to the bottom, and change the semicolons into curly brackets. And now all these need to do is return their respective values. So return free memory, return used memory, and return reserved memory. And we just need to put in our page frame allocator : little detail. Alright, compile again just for sanity, and that should be good. Now we can use our page frame allocator and see how much system memory we have, how much is reserved, and how much will be used. So let's create an instance of page frame allocator. New allocator. We need to include page frame allocator.h. And now we need to do new allocator dot read EFI memory map. We need to pass it the memory map, so boot info memory map. We need the memory map size, boot info memory map size, and boot info memory map descriptor size. And now we can print the system memory. So now we can do new renderer dot cursor position equals 0, new renderer dot cursor position plus 16, just to make sure we have a new line ready to go. I really should put this into its own function, but I'll get to that eventually. And now we can print new renderer dot print free RAM. Then we can do new renderer dot print to underscore string new allocator dot get free RAM, and that's a function, so we need our brackets at the end of it. And now we can print space KB space, and then we can go to our next line. So we'll just copy the next line that we have there. And before we go any further, we need to divide the get free RAM by 1024 so that we have the KBs instead of the singular bytes, because if we're displaying the bytes, it's going to be a little bit messy. So we'll display kilobytes. Alright, now we can copy these 4 lines 2 times. So we have the used RAM and the reserved RAM. So we can get used RAM and get reserved RAM. We need to do cursor position dot y plus 16, not just cursor position plus 16. Now we can compile that and do make build image. Now, as you can see at the top left of the screen, we have 227 megabytes of free RAM. We've used 12 kilobytes to store our bitmap, and we have 36 kilobytes of reserved RAM. So that includes things like unusable RAM and ACPI reclaimable memory. So that's fine. We can increase or decrease the amount of memory that Kimu has access to. So we can changing the memory to 2G, so 2 gigabytes. And then running that, we should have a completely different reading. So we have 2062 megabytes of free RAM available, which is 2 gigs. We've used 68 kilobytes to store our page frame bitmap. And we have 35.9 reserved megabytes of RAM. Now that our page frame allocator seems to be working okay, we can create a function for it to actually be able to give us a free page for us to use in our page tables to extend the memory of our processes. So we just need to create one more function. We'll call it void pointer. We need to get a pointer to the address that we're allowed to use. Request page. Now back in page frame allocator.cpp, we can create the implementation. So void page frame allocator : request page. Now I'm going to create a very simple request page function that has a lot, and I mean a lot, of room for optimization, but it's going to work. So for uint64t index equals 0, index less than page bitmap dot size times 8, index plus plus. And now we just go through all of the indexes in the bitmap and find a free page frame. So if page bitmap indexed by index equals true, continue. So if it is not a free page frame, we continue on to the next page frame. Otherwise, we lock the page, casted to a void pointer, index times 4096. So we lock the page that we have just found with our request page function, and then we return, casted to a void pointer, index times 4096. So now we're returning the memory address of the new free page frame. If we get to the end of page bitmap.size, we're going to exit this loop, and then we've run out of page frames that we can allocate, in which case we're going to need to do a page file swap, which is saving some memory to the disk to free some RAM. But since we don't have a hard disk driver yet, we're not going to be able to do that. So we just need to return null and then make a note that we need to do page frame swap. So page frame swap to file. And this void needs to be a void pointer. Alright. I'm just compiling that just to make sure I haven't made any mistakes. And now we can request some pages. So let's request something like 20 pages and then print their addresses to the screen. For int t equals 0, t less than 20, t plus plus. So we're going to do it 20 times. New allocator dot request page. Void pointer address equals new allocator dot request page. And now we can copy just 2 lines of our new renderer. And now we need to print I like to print to H string. Just makes it easier to read. Cast it to a uint64t address. Alright, now we can see what that does. So we compile, build image. Now as you can see, we have printed the addresses of our page frames to the screen that we've allocated. None of them are repeated because we've locked them after we've requested them, so we don't have any collisions. So that's working as we need it to. There is one more thing we need to do before the end of this video, and that is to reserve the memory used by the kernel. And to do that, we need to know the start and the end of the kernel. So we need to create some linker variables. So we'll go into our workspace directory, enter our kernel.ld file, and create our variables. So just before the text section, we'll do underscore kernel start equals dot semicolon. So we're just setting kernel start to be at this address. And at the end, we will do kernel end. Kernel end equals dot semicolon. Alright, we can close that now. And in kernel.cpp, we can reference these variables. So we can do extern uint64t underscore kernel start. And then we can do the same with kernel end. Alright, now we can use those to get the start and the size of the kernel. So uint64t kernel size equals uint64t reference to kernel end. We need to get a reference so that we get the memory address minus uint64t a reference to underscore kernel start. So now that gives us the size of the kernel. We can now get the amount of pages that the kernel will take up. So uint64t kernel pages equals uint64t kernel size divided by 4096 plus 1. So that gives us the amount of pages we need. Now we can use our page allocator to lock those pages. So new allocator dot lock pages reference to kernel start and kernel pages. So we can move this up to before we print our addresses, just to see how that changes things. We'll make kernel and we'll make our image. Now before I get any further ahead of myself, I'm going to change this back to 256M, so I'm not using 2 gigabytes every time I run QEMU. Now as you can see, the addresses printed by our request page function now start from 4000 instead of 1000, which indicates that our kernel, starting at 0, has been locked away successfully, and we are using 16 KBs of RAM. Now we can increase the bloat of our kernel just to see what will happen. So we'll create an array, we'll call it a uint64t bloat, and we'll make this array a size of 60,000. We'll create our kernel, create our image. Now as you can see now, the requested page frames now starts from 79000. So that has bloated our kernel significantly. Now one thing I noticed is the used RAM is still 16 kilobytes, which isn't correct, so I'm just going to have to fix that one real quick. Actually, everything is working fine. It's just that what I suspect is happening is it's being reserved in reserved pages when we're doing this, so that when we're going to lock it again, it's not locking it because it's already reserved. It's probably reserved because UEFI regards where the kernel is loaded as some UEFI memory, so it wouldn't be EFI conventional memory, and so we're reserving it. So it's working fine. We just need to lock pages to make sure 100% that the kernel is locked away so that we don't have any memory collisions in the future. We'll get rid of this bloat just to make sure that we don't leave it in for the rest of the series. That'll be it for this video. I'd like to thank you for watching, and I will see you next time.